viewers, welcome to the Chem is Try channel. If this is your first time to join me on this channel, my name is Chiposhot Game. Please subscribe, like and share. Today we are going to look at electrochemistry, and our main objectives that we want to cover today. We want to define electrode potential. Let's see how an electrode potential is set up. We want to define standard electrode potential, the E0 values or E theta values. We want to define what is the standard cell potential. We also want to look at the sheet, that is the standard hydrogen electrode. We want to describe the sheet and how we use it to determine the E0 values. We also want to look at the methods which are used to measure the standard electrode potentials of metals as well as non-metals which are in contact with their ions in aqueous solution. And also want to describe how we can measure the E0 values of ions of the same element, but they have different oxidation states. And finally, we want to see how we can calculate the standard cell potential by combining the standard electrode potentials of the half cells which will be involved in creating the cell. So let's start cracking. When we have a metal, which is dipped, a metal dipped in a solution of its ions, let's make it zinc, and here in the solution we also have zinc ions. What is happening here? The metal, it has a tendency of losing electrons. It has a tendency of losing electrons so that it forms this. But the ions also, which are already in solution and those which are being introduced, they also have a tendency to receive the electrons. To reform the metal. Hence, we can say at a certain point we are going to reach an equilibrium for this reaction. One is showing the potential to give electrons, the other is there's the potential to receive. The solution is the potential to receive the electrons, the electrode is the potential to give the electrons. So there is now going to exist a potential difference. There is now a potential difference between the electrode and the solution of its aqueous ions. This is what we now refer to as the electrode potential. So, in simple terms, the electrode potential is the potential difference of a metal or species. The potential is the potential difference between a metal or a species and its aqueous ions. Its aqueous ions. Between a metal or a species and its aqueous ions. This is what is referred to as the electrode potential. Is it possible for us to measure the electrode potential of this half cell? Let's suppose we take another wire, we connect a voltmeter there, and we dip the other end of the wire. Are we going to obtain the potential, the electrode potential for the zinc plus half cell? When we make use of a wire is already another species, or it's another metal which also has, or which also sets up its own electrode potential, because the metal will dissolve, will undergo oxidation, and the ions of the metal which are formed will then undergo reduction. So the metal itself is also going to set up its own electrode potential, so much that the value that you obtain on our voltage, there is not actually the electrode potential for the zinc system, but it is now going to be the potential difference between the half cell created by the wire and the half cell of the zinc. So it's already a cell potential. It's no longer an electrode, but it's now a cell potential, because two half cells combined together now gives us a cell. So the wire is creating its own half cell. The zinc is its own half cell. So when these two half cells combine, the voltage reading there is now giving us the difference between the two cells. So in actual fact, what we are simply saying here is, it is not possible for us to measure directly the electrode potential of a metal dipped in an aqueous solution or a non-metal dipped in a solution of its own ions. Hence, there is need for a standard which can be used as a reference point. And the standard which is chosen or which is used is the standard hydrogen electrode. So let's look at the shape. So right now we are describing the shape. So the standard hydrogen electrode is a half cell whereby we have 1 mole palladium cubed H+ ions and bubble the hydrogen gas into this system. We introduce the hydrogen gas through there, and it will be at a pressure of 1 atmosphere, and the whole system should be at a temperature of 298 kelvins. And we are going to use a platinized platinum as our electrode. And so our electrode is platinum and yet platinized, and this is your salt bridge, and this is your voltmeter of high resistance, so that it only measures the potential but will not allow the electrons to flow. So this is the standard hydrogen electrode. So the electrode reactions which are taking place here this is the reaction that is occurring in this half cell. And upon agreement, the E0 value, the electrode, the standard electrode potential for the hydrogen half cell is given an E0 value which is of 0.00 volts. This is now our reference. Why are we now saying it is standard? We are operating under standard thermodynamic conditions. We are using, for all concentrations, the solutions must have a concentration of 1 mole palladium cubed. We are also using temperature of 298 kelvins and pressure of 1 atmosphere. These are the standard conditions. And because we are operating under standard conditions, so the standard electrode potential for the hydrogen half cell is now 0. So in order now to obtain the standard electrode potentials of the metal dipped in a solution of its own ions, we must now compare the standard electrode potential of that cell relative to the sheet. And how can we now define the term standard electrode potential? It is the potential difference of a metal which is dipped in 1 mole per dm cubed solution of its ions compared to the standard hydrogen electrode. This is our sheet. So all the other measurements we are going to compare to the sheet. And when it is now a cell potential, we are now looking at the potential difference of 2 half cells under standard conditions. That is now the cell potential. So let's see, take for example, how we can now measure. How can we now measure the standard electrode potential of, say, iron in a solution of iron 2 sulfate? So we are going to determine the standard electrode potential of iron and Fe2+. We are going to use iron 2 sulfate. So we need to form the half cell for the iron system. And because iron is a metal, it can be furnished into an electrode. And we now have 1 mole per dm cubed Fe2+, and this is our Fe. And then we make use of connecting wires. We connect it to the voltmeter, and we continue with our salt bridge. So how are we going to obtain the standard electrode potential of the iron 2 system? Since the half cell, the sheet half cell, is an E0 value of 0. What it now means is whatever reading we are going to obtain on our voltmeter will now be the standard electrode potential for the iron 2 system, which will be represented by this equation. So please note, our E0 values as given in the data booklet are written as reduction potentials. And this one will now be minus 0.44 volts. That's the E0 value, which is allocated to that. So that is how we obtain the standard electrode potentials, or how we determine the standard electrode potentials of a metal in contact with a solution of its aqueous ions. Let's now look at how we can determine, for example, chlorine, which is now a non-metal. Chlorine gas in contact with the chloride ions. Let's see how we can obtain. Remember, all standard electrode potentials, we are now going to obtain them relative to the sheet. So we have our half cell container, the electrolyte 1 mole per dm cubed, this time of Cl- ions, and because it's now chlorine, it's a gas, it cannot be furnished into an electrode and it will vaporize, or it cannot be channeled into the container. So we use the dumbbell structure, the same as that one we've used for the sheet platinized, and we introduce our chlorine gas from there, 1 atmosphere pressure, 298 kelvins. So whatever reading that is going to be obtained on the voltmeter compared to the sheet is due to this reaction. And for this one, the E naught value is plus 1.36 volts. For the ion, Fe2 plus 2 electrons to give us Fe, we said it was minus 0.44 volts. Some are negative, others are positive. What's the implication? If the E naught value is positive, it means energetically the forward direction is favored. The forward direction is energetically favored. But if the E naught value is negative, then it means the forward direction is not energetically favored, but the backward direction is now the one which is favored. Because when you reverse the reaction, you are also going to reverse the charge. Please take note of that. So the reading on the voltmeter will be plus 1.36, simply because the She is an E naught value of 0. So whatever value you are going to obtain from the voltmeter is now the value for your half cell, which will determine. So for this chlorine, since chlorine cannot be furnished into an electrode, it also now means we must use platinum, which is an innate electrode. Platinum is an innate electrode. We use it to make electrical contact. But it is platinized because these reactions are going to occur on the surface of the electrode. So it is platinized to increase the surface area because platinum is also going to act as a catalyst. This is the dual functions of the platinum during these reactions. That's the reason why it is platinized, to increase the surface area so that the gases can absorb onto the catalytic surface, and this reaction is also made to be faster. Okay, so let's now look at how we can determine the standard electrode potential of ions of the same element with different oxidation states. Let's consider the ion 2, ion 3 system. Okay, so we are going to put one more per dm cubed of Fe2 plus. We also put one more per dm cubed of Fe3 plus into our container. Then we are going to use platinum electrode for electrical contact. And this is a connecting wire. And the whole system should be 298 kelvins. And we then connect to the sheet. Whatever reading which is obtained on the voltmeter will be true to this reaction. And it's normally plus 0.77 volts. That's the value which is given in your data booklet. Okay, so basically this is how we measure, how we can determine the standard electrode potentials of the different systems. Now let's see how we can now construct an electric cell using different half cells. These are now the galvanic cells. We want to make a cell by connecting ion 2, ion 3, and we connect it, let's say, with the zinc. So we use zinc, this other end, so we need zinc, and the zinc ions, one more per dm cubed of zinc 2 plus. Any soluble salt of zinc will do, zinc nitrate will do, and this is our zinc electrode. And of course, we need our salt bridge. What's the function of the salt bridge? Food for thought, because it is always there. What purpose does it serve? What is it made of, the composition. Think about it. So, this is the cell that we've created. So for the zinc, the reactions, the electron potentials occurring will be these ones. And the E naught value there is minus 0.76 volts. If I'm not mistaken, let me double check with the data that we use. So we have to go where the species which we are dealing with are involved, and therefore for the zinc there it is, and that is the E naught value in the reduction equation. In the ion 2, ion 3, it is here. I think ion 3 going to ion 2, that is the E naught value. That is where I obtain the values that you have seen me writing on the board. That's how you determine. Now, the question now is, who is oxidized, who is reduced, so that we can end up calculating the E cell. Who is oxidized, who is reduced. We'll talk more in detail in the next segment, but for today, just know that the E naught value, which is more negative, is the one that must undergo oxidation so that we reverse. So in this case, the zinc is the one which must undergo oxidation. So they have the reaction which is occurring at the zinc 2 plus electrode is now this one. And it now means the reaction which must occur at the ion end is now this one. And for the zinc we have reversed. So if we have reversed the reaction, it also means we have reversed the charge. So instead of being negative, now 0.76, and this one we've taken it just the way it was, we've not reversed anything. So we take the E naught value as it is, which is plus 0.77. Now, for me to find the E cell, I simply now combine the two. So I'm adding 18, 3 carry 1, 14, 15. So at the end, the E cell, which is generated by combining these two half cells, is 1.53 volts. So if we were to take these and make them, punch them into a battery or a cell to give us electrical energy, then that is the voltage one cell will produce. And if you want to create greater voltage, then it now means you have to connect these cells in series. So for today, this is how we determine, and also this is how we calculate the E cell. So this value here is now the E cell, the standard cell potential, which we said is the potential difference between two half cells under standard state conditions. Cell 1, half cell 1, and the second half cell. This, when you combine them, they now give us the standard cell potential, which is now plus 0.76 plus 0.77, and voila. And we can also now be asked to write the overall reaction which is taking place. Suppose we mix these together in the same container. What type of reaction is going to occur? So for us to find the overall equation, it's now very simple. Reaction, we now take the two half cells. The two half cells, they are already balanced in terms of atoms and charge. Now we simply need to balance them them in terms of electrons. When we combine two half equations, we balance now the electrons. The number of electrons given should be equal to the number of electrons gained. So 2 electrons, there only 1, so we must multiply the ion system by 2. And therefore, it now zinc plus 2 Fe 3 plus. 2 electrons were produced, now 2 electrons were consumed. So the electrons, they are now out of the picture, and then I now take the products, zinc 2 plus plus 2 Fe 2 plus. This is now the overall reaction which is now taking place. That's how we now combine or make use of the half equations to construct the redox equations. So we've come to the end of our lesson today, but our homework: composition of the salt bridge and function of the salt bridge. Please subscribe, like, and share.